Hello everyone. In this hour we are going to talk about fluid dynamics. If you have came here, I assume that you have already seen fluid statics because a little bit of a part of fluid statics will be used in fluid dynamics. Now, in fluid dynamics, first we will talk about fluid dynamics and then we will talk about viscosity. When I talk about fluid dynamics, we will focus here predominantly only on two equations. The equation of continuity and the Bernoulli's equation. Both are simple and this particular topic is super scoring. So without wasting time, let's start learning fluid dynamics. So first of all, which type of fluids we are talking about and what exactly is a fluid? The things which flow are called fluids. So when I say the term fluids, it means gases and liquids. And I told you, even in fluid statics, we are not at all talking about gases. We are talking actually about liquids, and these liquids which we are talking about should have some special property. So the fluids we talk here are of a particular nature. Which nature? The fluids we talk here are incompressible in nature. When I say that a fluid is incompressible, it means that it can't be compressed. So you can't decrease its volume. You can't change its density. Now, if you have got gases, you know that gases can be compressed as well as expanded. So definitely we are not at all talking about gases here. So we are talking about liquids. And those liquids are of special type. Those liquids are incompressible in nature. Now when I say that a fluid is incompressible in nature, so it can't be compressed. So the volume of the fluid remains constant. And once you know that the volume of the fluid remains constant, you can even say that the density of an incompressible fluid has to be constant. So the volume remains constant as well as the density of the fluid remains constant. The another property of the fluid which we are talking about here is that the fluid should be non-viscous. When I say that a fluid is non-viscous, it means that when the fluid flow layer over layer, there is no force between the layers of the fluid. Such a fluid is called non-viscous fluid. And the fluid which has got both of these properties, which is incompressible as well as non-viscous, is combinedly called as irrotational fluid. So the fluid which is incompressible as well as non-viscous, also called ideal fluid, is also called irrotational fluid. So now without wasting time, let's talk about the first important equation of fluid dynamics, that is the equation of continuity. So what does the equation of continuity tells us? If we have a tube of non-uniform cross-sectional area, as you can see that going from left to right here, the cross-sectional area decreases. On the left hand side, the cross-sectional area A1 is more, while on the right hand side, the cross-sectional area A2 is less. So if on going from left to right, the cross-sectional area decreases, how does the velocity of the fluid change? I know that most of you already know what is the equation of continuity, but it's my job to explain it one more time. So the type of fluid we are talking about here is incompressible fluid. If the tube is completely filled with fluid, so if this tube already contains fluid completely filled through it, then there is no more space to fill up fluid. And if the fluid flows through this particular part of a tube, then the rate of volume in should be equal to rate of volume out. If beta somebody says no sir, volume in should be greater than volume out, it means that this particular part of tube is storing the fluid. If somebody says that the rate of volume out is more than the rate of volume in, it means that this particular part of tube is creating fluid. That can't happen. So if this is a part of a pipe of variable cross-sectional area, despite having a variable cross-sectional area, I can say if this tube is completely filled and the fluid is incompressible in nature, it can't be compressed, then the volume coming in should be equal to the volume going out. So this is high time that we talk about a term called volume flow rate. So the symbol we use for volume flow rate is Q. The terminology itself says volume flow rate, the rate of flow of volume. So d volume upon dt. I'm not writing dv upon dt because I know my kids are smart, they will start treating it as acceleration. So d volume by dt. Now question is, what is the volume flow rate for a tube of cross-sectional area A through which the fluid comes out with a speed v? So volume flow rate, the rate of flow of volume, which is denoted by the symbol Q. So you will say, in an infinitely small frame of time dt, The infinitely small length of fluid coming out will be equals to V into dt, because the speed of fluid is V. So in an infinitely small frame of time dt, the length of fluid coming out will be V dt. So the infinitely small volume of fluid coming out will be equal to the cross-sectional area times the length of fluid coming out. The cross-sectional area is A and the length of fluid coming out in an infinitely small frame of time dt is V dt. So from here, bringing the dt down on the left hand side, you will say the rate of flow of volume with respect to time is given by nothing but the cross-sectional area of the tube multiplied by the speed of the tube. So the volume flow rate equals to the rate of flow of volume with respect to time is nothing but the cross-sectional area into the velocity of fluid. So volume flow rate can be written as the cross-sectional area at that place of the tube multiplied by the velocity of fluid. Now, since we know that the volume coming in has to be equal to the volume going out, so the rate of flow of volume in has to be equal to the rate of flow of volume out. For this particular tube, you will say that the rate of flow of volume in has to be equal to A1 V1, and this has to be equal to the rate of flow of volume out, that will be A2 V2. Hence we can say bachon A1 V1 has to be equal to A2 V2. Now, since we know that A1 V1 equals to A2 V2, if we think of any small cross-sectional area here, random area A, where the velocity is V, I can say that if at any cross-sectional area, the area is A and the velocity is V, so for this particular flow, everywhere the product of area times the velocity remains constant. So this particular equation I have written is called the equation of continuity. So let's see a question based on the equation of continuity. Question goes like, determine the rate of flow of fluid in the third pipe. So there are three pipes which are joined. The first pipe having a cross-sectional area A, in which the fluid enters with a speed V. The second pipe of cross-sectional area 2A, from which the fluid exits with a speed 2V. And the third pipe has an area A by 2. They are asking what is the speed of the fluid entering or exiting into this pipe. Now sir, how will I know that the fluid is entering or exiting? Do not think so much. Just assume that the fluid is entering, let's say with a speed U. If you have made wrong assumption, your answer will be negative. So if U comes out to be positive, it means that what you have assumed while solving is correct. And if U comes out to be negative, it means that what you have assumed while solving is incorrect. So you should flip the direction. So do not waste time thinking that the fluid is actually entering or exiting the third pipe. So we can say, assume that water flows in the third pipe at a speed U. So the water flows with a speed U into the pipe. Now, for this particular pipe, the T-shaped pipe with a junction, you will say the volume flow rate in has to be same as the volume flow rate out. So if here the fluid enters with a speed U, the volume flow rate in has to be same as the volume flow rate out. So volume flow rate in equals to volume flow rate out. The volume flow rate in will be V into A plus U into A by 2. Both are coming in. And the volume flow out has to be 2A into 2V. For any tube having a cross-sectional area A, from which the fluid comes out with a speed V, we say that the volume flow rate is nothing but A into V. So using the same concept here, so we will say the volume flow rate in will be V into A plus U into A by 2. This will be the volume flow rate in. And the volume flow rate out will be equals to 2V into 2A. So bachon, here you can cancel out A, or without even cancelling, you can write U equals to 4VA minus VA, which is 3VA upon A by 2. On the right hand side, you have got 4VA, 2V into 2A, 4VA minus VA, that becomes 3VA upon A by 2. So A get cancelled. This 2 moves from denominator of denominator to the numerator. So U comes out to be equals to 6V. So a simple question, right? Let's move on. Now we will talk about Bernoulli's equation. Now I said that there are just two equations to understand. We have talked about one of them already. This is the second one. So I want your 100% attention when I explain the Bernoulli's equation. And if you haven't mugged up the formula till now, this is the time to mug it up. So let's say we have got this tube of variable cross-sectional area, as well as the center line has got variable height above the ground. So the center line of the left end is at a height h1 and the center line of the right end is at a height h2. Since, as you can see, the cross-sectional area is not same, the speed of the fluid is not same. Here the speed is v1, here the speed is v2. As well as, let's assume the pressure in the fluid at this position is P1 and at the second position is P2. What does the Bernoulli's equation tells us? It says that P1 plus rho g h1 plus half rho v1 square has to be equal to P2 plus rho g h2 plus half rho v2 square. From where does we get this particular equation? This equation comes from work energy theorem. Just remember that this equation comes from work energy theorem. Since it comes from work energy theorem, it can't be applied on a non-viscous fluid. That's why every time you apply Bernoulli's equation, it must be applied on a non-viscous fluid. Moving on, there is another way to say the same equation. If you look at any random cross-sectional area A, where the speed of the fluid is V, where the pressure is P and the height of the center line of this stream above the ground is H, you can say for this particular flow, if it's a non-viscous incompressible fluid, I can write P plus rho GH plus half rho V square equals to constant. So you look at any given cross-sectional area, look at the pressure of the fluid, look at the height of the fluid above the ground, and look at the speed of the fluid, and you can write the terms P plus rho GH plus half rho V square, and that will be the same for the entire stream. So P plus rho GH plus half rho V square equals to constant for a incompressible non-viscous fluid flowing. Now here question is, what is pressure? So pressure, the force per unit area. How can you write pressure in terms of work? In the chapter of KTG and thermo, we have learned that the work done equals to pressure times volume. So can I say that pressure represents work done per unit volume? Pressure represents work done per unit volume. What does rho GH represent? So rho GH, we know that mgh is potential energy. If I divide potential energy with volume, what I get is this mass upon volume can be written as density. So rho GH is nothing but potential energy per unit volume. Rho GH is nothing but potential energy per unit volume. Once more, what can we think of pressure as? The work done per unit volume. What is rho GH? Potential energy per unit volume. What we can think of half rho V square as? So we know that half mv square is kinetic energy. So if we divide both the side with volume, so mass upon volume becomes the density. So we can write half rho V square to be same as kinetic energy per unit volume. So the first term here is work done per unit volume, second term here potential energy per unit volume, and third term here kinetic energy per unit volume. So essentially Bernoulli's equation comes from principle of conservation of energy. It is energy conservation, or you can say it comes from work energy theorem. Now remember that here each term has dimension same as that of energy per unit volume. Each term represents energy per unit volume. Yeah, the pressure represents work per unit volume, but work energy theorem tells us that work can be converted into energy. There is one more way to write the same Bernoulli's equation. If we divide each term with rho g, if we divide each term here with rho g, so this first term after dividing with rho g becomes P by rho g. The second term becomes rho g h by rho g, that becomes h. And the third term here becomes half rho v square by rho g, which becomes v square by 2g. And this also has to be equals to constant. So we can even write this equation as P by rho g plus h plus v square by 2g equals to constant. Now understand that here each term has got dimension of length. You know that P equals to rho gh? Yes sir. So P by rho g will have the same dimension as the length now. So P by rho g has got dimension of length, height has got dimension of length, and v square by 2g, you have learned that if a ball is projected upward with a speed v, On a planet where the acceleration due to gravity is g, then the maximum height attained by this ball is nothing but v square by 2g. So this v square by 2g also represents kind of a length. Now, engineers use these terms all the time rather than using p plus rho gh plus half rho v square equals to constant. So since engineers use these terms, many engineers are involved in paper making. So beta, they might ask you question based on this particular format. So you need to remember what is the name of these three terms. P by rho g is called pressure head. P by rho g is called pressure head. So they might say there is a fluid of density blah 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 at a place, the pressure is this much. What is the pressure head? So pressure head is not pressure. Pressure head is the pressure at the point upon the density divided by g. That's called pressure head. So you need to divide each term here with rho g so that each term gets the dimension of length. The term h is called gravitational head. Isn't it so easy? mgh is the gravitational potential energy. Gravitational energy per unit volume gave you rho gh, and when you divide it with gh, what you get is h. But this whole term came from where? Gravitational potential energy, right? So this term h, the height of the fluid above the ground, is called gravitational head. And the third term here is called kinetic head or the velocity head. Now why it's called velocity head? Because it is because of the velocity. So if the velocity of fluid at any place is v, we say that the velocity head of fluid at this place is v square by 2g. So remember that in this particular format, each term represents the dimension of length, and this is another way of writing Bernoulli's equation. Now moving on, from the equation of continuity, it doesn't matter that the fluid level rises up or goes down. We get the equation of continuity from volume conservation. If the fluid flowing in this tube is incompressible, then the rate of volume of fluid coming in has to be same as the rate of volume of fluid going out. So we can say with %% guarantee that the volume flow rate, which is equals to AV, has to be equals to constant. So for any given cross-sectional area, if you multiply it with the speed, you do it here, you do it here, you do it here. Look at the cross-sectional area and multiply with the speed of the fluid there. That remains same for the entire tube. So you say the flow rate in this entire tube, which is nothing but cross-sectional area times the velocity of fluid, remains constant for the entire tube. So this is from the equation of continuity. More. So we can say A1V1 equals to A2V2 equals to AV, which is constant. Now remember that Bernoulli's equation is energy conservation. It comes from work energy theorem. It is essentially principle of conservation of energy. It works only on non-viscous and incompressible fluid. You shouldn't apply Bernoulli's equation on viscous fluid. Why? Because in case of viscous fluid, there are viscous forces and there will be some energy loss. So you should not apply Bernoulli's equation on viscous fluid. So now since we have learned the two equations that we needed to learn, now what we are going to do is application of them. So without wasting time, let's start. The first question goes like, there is a tap, okay, and from the mouth of the tap, the fluid comes out with a speed u. The mouth of the tap has an area A. Question is, as the water falls down from a tap, the stream becomes tapered. It keeps on becoming narrower and narrower, and you have observed this in your house, right? The stream of the flow keeps on becoming tapered. Somebody asks you why, you will say from equation of continuity. As the fluid falls down, its speed will increase. Yes. So I can say that V has to be greater than U. Yes. If here the cross-sectional area is capital A, and I assume that here the cross-sectional area is small a, from the equation of continuity, U into A has to be equals to V into small a. As V is greater than U, the velocity increases, so the cross-sectional area should decrease, and that is the reason as when you open the tap, as the water falls down, the stream keeps on becoming more tapered and tapered, more thinner and thinner. So now here, as the water falls down from a tap, the stream becomes tapered. Determine the cross-sectional area of the stream at a distance h below the tap, given that the water stream comes out of the tap from the cross-sectional area A with a speed u. So you need to tell what will be the cross-sectional area of the stream here. Sir, I can find cross-sectional area easily using the equation of continuity given that I know what is the velocity of fluid here. And to find the velocity of fluid here, what's going to help you is called Bernoulli. So you will say, as the fluid falls down, let's say after falling down through height h, the fluid has a velocity v, and let's say this fluid has a cross-sectional area A. So from the equation of continuity, AU equals to AV, the area here into the velocity here U has to be equal to the area here A times the velocity here V. So AU equals to AV. Now how to find V in terms of U, H and G? Beta, when I was in class 11th and I saw this question for first time, I did it by mistake without using Bernoulli. And then I realized, okay, in the type of questions which get asked from us, you do not have to apply Bernoulli in most of the cases. So what I did by mistake was, I thought that, okay, the fluid is falling. It's kind of free fall once coming out of tap. If after falling through a length h, it attains a speed v, we can use the third equation of motion and we can say the final velocity square minus initial velocity square equals to 2 times acceleration into displacement. So the final velocity has to be equals to under root of u square plus 2gh. And when I looked at the answer doing this, I found that it's the right answer. So for the type of question which is coming in NEET, you can just keep on doing your third equation of motion. So AU equals to AV. But we will learn to apply Bernoulli's here. So from the Bernoulli's equation, since at both the places the fluid is exposed to atmosphere, here the pressure in the fluid will be P18 as well as here the pressure in the fluid will be P18. Do not think that as you will move down, the pressure in the fluid will increase. Why? Because the fluid lower is not at all supporting the weight of the fluid above it. If you have a tank filled with fluid, then as you move down, the pressure increases, no doubt. Because the fluid down here supports the weight of all the fluid above it. So the pressure keeps on increasing as you move down. But in this case, the fluid down here does not support the weight of the fluid above it. All the fluid keeps on falling. And since all the fluid is exposed to atmosphere everywhere, the pressure remains equals to P18. Now, to write the Bernoulli's equation, we have to assume some reference height from where we measure all the height. So I'm taking the lower level as the reference and we will measure all the heights from here. To write the second term in P plus rho g h, to write the height, I am taking here as the reference line. So for the first place, you will write pressure as P18, rho g into height h plus half rho u square. So this will be the left hand part of your Bernoulli's equation. For the right hand part, you will say here also pressure is P18. But here the height of the fluid is 0 because this particular level has been taken as the reference place from where we are measuring the height. So P18 plus rho g into 0 plus half rho v square. So P18 plus rho g into 0 plus half rho v square. So once you have this, you can cancel out P18 with P18. And this term of rho g into 0 is useless. It's 0. Now if you cancel out rho in each term and multiply each term with 2, what you get on the left hand side is 2gh plus u square equals to v square. Or beta v equals to under root of u square plus 2gh. Now here I feel like saying I told you so. This is just like free fall of water and you can directly make the third equation of motion. So on solving we get v equals to under root of u square plus 2gh. Once you know the velocity here, you can find the cross-sectional area from the equation of continuity. So you will say a into u equals to a into under root of u square plus 2gh. So this area A comes out to be AU upon under root of U square plus 2GH. Easy? So now let's see another application of Bernoulli's equation. Let's say we have this tank with a small hole at its base. Now question is, what will be the speed of the fluid coming out from this small hole at its base? We can see that the fluid has been filled up to a height h. As the fluid comes out, definitely the top layer of the fluid will move down. So we have assumed that the top layer has a downward speed u. How to write the Bernoulli's equation from the top layer till the fluid coming out? Do understand that both the top layer as well as fluid coming out are exposed to atmosphere. So pressure at both the places will be P18. To write the Bernoulli's equation, we always have to choose a reference height, the place from where we measure the heights. So we have taken that reference height as the base level of the tank and writing the Bernoulli's equation from top layer till the time the fluid coming out. So for top layer, you will write PATM plus rho GH, the height above the reference line is H, plus half rho U square, because the speed of this top layer is U, equals to PATM plus rho G into 0, because the height is 0, plus half rho V square. Now here you can cancel both the side PATM, and you will get rho GH plus half rho U square equals to half rho V square. Again you will say, okay sir, this is as good as cancel every term rho, and you will get on multiplying 2GH plus U square equals to V square. So if the speed at the top is U and after coming out here the speed is V, so V square equals to U square plus 2GH, just like we have learned in the third equation of motion. Now from equation of continuity, you can say that the area at the top multiplied by speed of the fluid at the top has to be equal to area of orifice multiplied by the speed of the fluid coming out. So AU has to be equals to AV. Now if you substitute the value of U here using the equation of continuity, you can find out the value of V. So you can say U has to be equals to AV upon A, the area of orifice multiplied by the velocity of a flux upon the area of the tank, the cross-sectional area of the tank. So rho GH plus half rho, in place of U I am writing AV by A whole square equals to half rho V square. Now cancel out each term with a rho, and multiplying 2, we can write 2GH plus A square V square by A square V square by A square equals to V square. Now you can bring this term to the right hand side, and you can write 2GH equals to V square times 1 minus A square by A square, or V equals to under root of 2GH upon 1 minus A square by A square. This will be the speed of a flux. But in our everyday life, the area of the tank is way greater than the area of orifice. So if the area of tank is greater than the area of orifice, this term right here tends to 0. Why? Because in numerator you have got area of orifice. In the denominator you have got area of tank. So this quantity A square by A square tends to 0. Very small quantity. So if you neglect this whole quantity, for the area of tank way greater than the area of orifice, you get 2GH equals to V square, or V comes out to be simply equals to root 2GH, which is as good as saying if I release a ball from a height h, then just before hitting the ground, its speed will be root 2GH, right? So again, a result very easy to remember. So if you have a tank, yes, and you have an orifice at a height h below the top layer, then the speed with which the fluid will come out is given by root 2GH, given that the area of tank is way larger than the area of the orifice. So now let's talk about range of the water jet. If rather than making the orifice at the very base, if we have made the orifice at some height d above the base, which means at some depth h minus d below the top, then what will be the range of this water jet coming out? So let's say this water jet after coming out falls at some distance r. How to find this value of r? Once the water jet comes out, it has got velocity only in the horizontal direction. So we can use the concept we have learned in the horizontal projection. So we have given it a horizontal velocity v, and it has been released at a height d above the base. At the time of the water jet coming out, it has got no vertical velocity. It has got only and only horizontal velocity. So since the initial velocity in vertical direction is 0, so as to find the time taken by it to fall down, we can use the second equation of motion in the vertical direction. In the vertical direction, till the time of landing, the vertical displacement is t. In the vertical direction, the initial velocity is 0. In the vertical direction, the downward acceleration is g. So you can write d equals to half gt square. So from here, you will get time taken to hit the ground. can be written as d equals to half gt square, or rearranging, moving this 2 up and g down and taking the root, you will say the time taken to fall will be under root of 2d by g. Once you know how much will be the time taken to fall, you can find out the range. The jet makes the horizontal displacement because of the horizontal velocity. And since there is no acceleration in horizontal direction, the horizontal velocity remains constant. So you will say the range has to be equals to velocity into time taken to fall. The velocity will be how much? Since we have made the hole at a depth h minus d, the velocity will be equals to root 2g into h minus d. Substituting the value of velocity and time, we will get the range to be equal to velocity root 2g h minus d multiplied by the time taken to fall, which is under root of 2d by g. Now, bachcho, you can cancel out this 2 and 2. Both the quantities are in root. This root 2 and root 2 after multiplying will give you root 4. So you will get range equals to under root of 4 into h minus d into d. Now, as the value of d changes, so does the range. Question is, for which value of d the range is maximum? So sir, for the range to be maximum, we will say h minus d into d should be maximum. And h minus d into d is maximum when d equals to h by 2. So you need to remember up this data. For the range to be maximum, d has to be equals to h by 2. It means that you must make the hole exactly midway in the tank at a height h by 2 above the base. Now if you make the hole at a height equals to h by 2 above the base, then what will be the range? So you will say the maximum range will come out to be, in place of d beta substitute h by 2. So you will get 4 into h minus h by 2 into h by 2. Now this h minus h by 2 becomes h by 2 into h by 2. So you get under root of 4 into h by 2 into h by 2. Alright. Now this 2 and 2 and 4 get cancelled. So what you get is under root of h square. So the maximum possible range comes out to be equal to the height of the fluid in the tank. So if they give me a question that there is a tank in which fluid is filled up to a height of 2 meters, okay, at what height above the base a hole must be made so that the range of the jet coming out of it is maximum? So I will say the hole must be made at a height of 1 meter above the base. And when you do so, the range of the jet is same as the height of the fluid in the tank, which in this case is 2 meters. So now let's see some important points about this fluid coming out of the orifice. The first case, if you make the hole at same distance from the base and from the top, the range of the fluid jet comes out to be same. Why, sir? We have learned that range equals to under root of 4 into h minus d into d. Now, bachcho, if you make the hole at a height x above the base, you will get range equals to under root of 4 into h minus x into x. If you make the hole at a height x below the top, then the height above the base will be h minus x. So you will substitute here the value of d as h minus x. So for this case, the range will come out to be under root of 4 into h minus x into h minus x. So that gives you range equals to under root of 4 into h minus x becomes x into h minus x. So in both the cases, the range comes out to be same. So look at this diagram and remember, if the hole is made at same distance above the base and same distance from the top layer of the fluid, then in both the cases, the range of the water jet comes out to be same. So if a hole is made at same distance from the top and bottom, the range for these water jets is same. And what has to be the value of x for maximum range? The range is maximum when x equals to h by 2. So while the range is maximum for x equals to h by 2, this is something that you have to remember. Moving on. Now, if from this tank, from this small orifice, fluid comes out, question is, what is the force by the fluid coming out on the tank? Or what is the force by the tank on the fluid so that it gets this velocity in the horizontal direction? Since the fluid gets some velocity, the fluid gets some momentum. If the fluid gets some momentum, there has to be some force acting. How much force? So we have done this in Newton's laws. If we have a tube from which the fluid comes out with a speed v, and the area of the tube is a, and first the fluid was at rest, So in an infinitely small frame of time dt, how much length of fluid will come out? The length of fluid coming out will be v dt. So the infinitely small volume of fluid coming out will be cross-sectional area into v dt. So the infinitely small mass of fluid coming out has to be equals to density into the infinitely small volume of fluid coming out. The infinitely small mass of fluid coming out equals to rho into infinitely small volume coming out, that is AV dt. This will be the infinitely small mass of fluid coming out. The infinitely small change in momentum of this infinitely small mass while coming out inside the tank, the fluid has zero velocity. Once it comes out, it has a velocity v. So the change in velocity is v. So the change in momentum of an infinitely small mass m coming out in an infinitely small frame of time dt will be the infinitely small mass coming out multiplied by the velocity with which it comes out. So the infinitely small change in momentum equals to rho a v dt multiplied by v. If you bring this dt down on the left hand side, you get dp by dt, which is the force, equals to rho av square. So remember that if a fluid which was at rest comes out from an area A with a speed v, and given that the density of fluid is rho, then the force on the fluid must be equals to rho av square. Okay, so here you will say force on the tank because of the fluid coming out, or force on the fluid because of the tank when the fluid comes out. From Newton's law, both will have the same magnitude. So force has to be equals to rho a into v square. You need to remember this. This is a useful formula. And in place of v, bachcho, you can substitute root 2gh. So the force comes out to be rho a into root 2gh whole square. So root 2gh whole square becomes 2gh. So you simply get rho a into 2gh. That can be written as 2 rho agh. So the force on the tank by the fluid coming out comes out to be 2 rho agh. Simple thing. Let's move on. So a question here. Question is, you have this pi of variable cross-sectional area. There are two cross sections, one where is a point A, second where there is a point B. Question is, if the fluid flows in the tube, where the pressure of fluid will be higher. So given that this fluid is incompressible and non-viscous, that's the type of fluid we are talking about, where the pressure of fluid will be higher, at point A or at point B. The common sense says that, sir, here the fluid will be moving faster now because the cross-sectional area is smaller. So where the fluid moves faster, the pressure has to be higher. But the answer is counterintuitive. Why? Let's see. As the cross-sectional area at A is more than the cross-sectional area at B, from the equation of continuity, we get that the velocity at B has to be more than the velocity at A. So here the fluid will move with less velocity, and here the fluid will move with more velocity. So the velocity of the fluid at B has to be more than the velocity of fluid at A. Now we can say from Bernoulli's theorem, P plus rho gh plus half rho v square equals to constant. P plus rho gh plus half rho v square equals to constant. Now both of them are at same height above the reference line. So this second term makes no difference. So what you need to focus upon is that for this horizontal pipe, the place where the cross-sectional area will be less, there the velocity will be high. Since the velocity will be high, v square will be high. And for this sum of these three terms to remain constant, if the velocity is higher, better the pressure has to be lower. So you have to keep this particular concept in mind. As the tube gets tapered, the cross-sectional area decreases. Since the cross-sectional area decreases, the velocity increases. Since the velocity at B will be higher, the pressure at B has to be lower. So at the place where the velocity is more for the same horizontal tube, the pressure has to be less because they have the same reference height, central line reference height. That's why the second term doesn't matter. So where the velocity is more, there the pressure has to be less. Hence, we can say that the pressure at B will be less than the pressure at A. The pressure at B will be less. Where the fluid has got more velocity, there the pressure will be less. And now we are going to look at many applications because of this particular effect, where the velocity will be more, there the pressure will be less. They might ask you, moving along the x direction, how does the pressure change? So if they ask you the pressure versus the distance diagram, So as the cross-sectional area keeps on decreasing, the velocity keeps on increasing. As the velocity keeps on increasing, the pressure keeps on decreasing. So when we plot the graph, the pressure keeps on decreasing. So keep this type of graph in your mind. So moving on, some important points which we get from where the velocity is more, the pressure is less. The first case, if this has been noticed when hurricanes come or wind blows at high speed, then the roof of the hut flies off. Why? So see, when the wind blows at high speed, the velocity of the wind increases. Yes. So the pressure will decrease as P plus rho G H plus half rho V square equals to constant. As the velocity increases, the pressure decreases. So on a windy day, the pressure inside the hut is PATM. But since for the outside air, the velocity has increased, the pressure has decreased. So outside pressure is less than PATM. So if you think of the shed of the hut, the roof of the hut, inside pressure is more, outside pressure of air is less. So because of this, a net upward force is created on the roof of the hut and the roof of the hut flies off. So on a windy day, the roof of the hut flies off because of the pressure difference created due to the difference in the wind velocity. Now, second example, which can be explained from here. If you take two pieces of paper and you blow air between them, what happens? The separation between them increases or decreases? When you blow air between them, as the air between them gets greater velocity, the pressure here decreases. But the pressure on the side outside is still PATM. So the paper tends to move closer to each other because on the two sides of paper outside the pressure is higher, while between the paper the pressure decreases. So the paper tend to move towards each other. So if you take two pieces of paper and you blow air between them, then the pressure between the papers decreases and the papers tend to move closer to each other. So when the wind is blown between two pieces of paper, the paper moves closer because of this very same effect. When the velocity increases, the pressure decreases. There is something called atomizer. So if you have got this device, which you might have seen in old movies used for perfume, there is this rubber ball. When pressed, air moves at higher speed through this piston. When this air moves at high speed, what happens to the pressure of air decreases. Because of this decrease in pressure, the fluid in the container rises up because the pressure on the top has decreased, creating kind of a suction effect. So here the pressure decreases. When you press the rubber bulb, the speed of the air here increases, because of which the pressure here decreases. So the fluid rises up and this fluid comes in the way of the air moving at high speed. So this air splits the fluid into small drops, and this device is called atomizer. So in an atomizer, when the air is blown, the fluid rises up and sprays because of the same effect. When the velocity increases, the pressure decreases. There are more examples to this. So the next point, ball turning its path in midair. Have you ever heard the phrase bend it like Beckham? A movie has been made by an Indian director based on this. So how does some footballer do this? Let's say this is the football field and these are the two goal posts. Some footballers can do this, that they can kick the ball from one corner and the ball keeps on turning mid-air and enters into the goal like a boomerang. You should see these trick shots on the YouTube after listening to the complete lecture. Okay, so how do they do it? They just do not provide ball with a velocity. They provide ball with both velocity as well as omega. Because of the angular velocity provided, at the top, the velocity will be v plus omega r. And at this point, the velocity will be v minus omega r. The rotational velocity at this lowest point will be backwards and translational will be forward. So because of providing the angular velocity, the velocity at the two ends is different. So the air which crosses them on the two sides also have slightly different velocity as the ball moves. Since the air have slightly different velocity, the air will have slightly different pressure, creating a net force on the ball in one of the direction. This is how they move ball in the midair, just by providing it velocity as well as omega. So as V1 is greater than V2, the ball starts to turn. Next, if we stand close to a moving train, so if there is a train passing by you at a high speed, then the air nearby the train also moves at a high speed and the pressure in front of you decreases, so you feel a pull towards the train. Similarly, if you are standing on a river bank, then let's say the river is flowing in front of you, so the air above the river moves with the river and you are standing on the bank. Since the air in front of you moves at a higher speed, it has a lower pressure, and the air behind you is at rest, so it has a higher pressure. So because of this difference in the pressure in front of you is less, the pressure behind you is more, so you feel a pull towards the river bank. So we experience a force towards them, towards a fast moving train or towards a flowing river. Now let's talk about one important device called Venturimeter. What is a Venturimeter? Venturimeter is a meter. It is used to measure what? Flow rate. So it is a device used to measure the flow rate. Now what does the Venturimeter consist of? It's a simple device with a variable cross-sectional area. So let's say you have got this tube in which the cross-sectional area keeps on changing. Now in this tube, tell me at point A and at point B, if the fluid flows through this whole tube, at which point the pressure will be higher? So sir, we have taken so many examples where the velocity is more, the pressure is less. Since at A the cross-sectional area is less, at A the velocity will be higher. So hence at A the pressure will be lower. And we just place two vertical tubes here so that we can measure the pressure difference. Since at point A the pressure will be lower, the fluid level in the tube connected to A will be less, while the fluid level in the tube connected to B will be more. So keep this small thing in mind. So this is something what the Venturimeter looks like. On the device itself, it is mentioned what is the ratio of these two areas, and we just need two things: the ratio of these two areas and the difference in the height in the two vertical tubes connected at these two different cross-sectional area, so as to know the flow rate. How? Let's see. You will say from Bernoulli's equation, the pressure at A plus rho GH means the height above the datum plus half rho VA square equals to the pressure at B plus rho GH plus half rho VB square. Since this tube is horizontal, the center line of both the cross section is at same height above the datum. So this second term in the Bernoulli's equation makes no sense. You can cancel them out. Now we will say the pressure at A plus half rho VA square equals to the pressure at B plus half rho VB square. So you can write half rho VA square minus half rho VB square, bringing it to left hand side, equals to PB minus PA. Now you can see at the point B, since the cross-sectional area is more, the velocity will be less. Since the velocity will be less, the pressure will be higher. You can write the pressure difference between these 2 points as the pressure created by this much height of fluid, and this is the same fluid, it will have the same density. So you will write this pressure difference simply as rho GH. So you will say half rho, taking half rho common, into VA square minus VB square equals to rho GH in place of PB minus PA. The difference in the pressure, we have written this difference in the pressure will be same as the difference in the pressure created by a fluid of height h. Now cancelling out beta rho and rho on both the sides, and from equation of continuity we can say velocity at A multiplied by area at A equals to velocity at B multiplied by area at B, right? So we can again write VA square minus VB square, cancelling out rho and rho, equals to 2GH. Now from equation of continuity, area at A multiplied by velocity at A equals to area at B multiplied by velocity at B. So from here you can say the velocity at B equals to the area at A into velocity at A upon the area at B. Now, if you substitute the value of VB here, you can find out VA. So, substituting the value of VB, we get VA square minus, in place of VB, write area at A into VA upon AB whole square equals to 2GH. Now, take beta VA square common. So, you get VA square into 1 minus area at A upon area at B whole square equals to 2GH, and you can bring this whole term of 1 minus area at A upon area at B whole square to the denominator, and then what you have to do is take the under root. So when you take the under root, you get VA equals to root 2GH upon 1 minus area at A upon area at B whole square. So I said that you need just two data. First data, the difference in the height, and second data, the ratio of the area. And once you know this, you can find the velocity of flow at the area A. And once you know the velocity of flow, you can measure the flow rate just by multiplying it with the cross-sectional area. So that's all in this part of fluid dynamics. Now let's move on to viscosity. So now we are going to talk about viscosity. Now what exactly is viscosity? The property of fluid by the virtue of which it opposes the motion between the fluid layers. So when a fluid undergoes laminar flow, the fluid flows layer over layer. Because of the difference in the velocity of two layers, there is a force acting between them. This particular force is called viscous force, and the property which gives rise to such a force is called viscosity. The first thing you need to know about viscosity is the temperature dependency of viscosity. What happens to the viscosity with the change in temperature? Now here we will talk about two things. We will first talk about liquids and then we will talk about gases. You have seen people constructing roads. So the coal tar, which when cool is very viscous, is very thick. To lay it down on road, what do? We heat it up. So when we heat up the coal tar, it becomes more fluid. It becomes more flowable. Why? Because the layer over layer motion becomes easy. Why? Because the viscosity decreases. So for liquids, when you heat them up, the intermolecular force decreases. As the intermolecular force decreases, the layer over layer motion becomes easier, and we say that the viscosity of the liquid decreases. So remember that for liquids on heating, the viscosity decreases. So for liquids, as the temperature increases, the viscosity decreases. But why is there a term usually? Beta, there is chemistry involved, the subject of exception. There are so many chemicals in this world. You might find a liquid whose viscosity increases on heating, but by and large, whenever you heat up liquids, their viscosity decreases. Now let's talk about gases. What happens to the viscosity of gases when they are heated? Sir, the viscosity of liquid on heating decreases. So for gas also it should decrease. No. Let's think that there are air molecules and an object is trying to move through these air molecules. When you increase the temperature of gases, the gases move at higher velocity. How do gases exert force on anything? By going, colliding and bouncing back. If these gas molecules will move with higher velocity, then on colliding and bouncing back, they will transfer more amount of momentum. When they transfer more amount of momentum, there will be more amount of drag force, there will be more amount of viscous force. So remember that for gases, as the temperature increases, the viscosity increases. Why? Because when you heat up gases, they start moving faster. When the gases move faster, on every collision with the object, they transfer more amount of momentum. Hence, there is more viscous force. It is tougher to move the object through the gases at the higher temperature. Now let's continue talking about viscosity and let's talk about Newton's law of viscosity. Let's say we have this river. We know that the river flows. So the top layer of the river moves. But do all the layers of the river move with the same velocity? Or is the river bed at rest? The fluid layer closest to the river bed has got zero velocity. While we know that the top layer of the river moves with certain amount of velocity. So we say that a velocity gradient is created in the river. As you move from the base of the river to the top, the velocity of the fluid keeps on increasing and the top layer has the highest velocity. So if you visualize two layers really close by, separated by an infinitely small distance dx. So if the layer below moves with a velocity v, then the layer above it at an infinitely small separation will move with an infinitely small amount of greater velocity. So the velocity will be v plus dv. Now just visualize these two layers. The lower layer moving with a velocity v, the layer above it moving with a velocity v plus dv. The upper layer moves faster compared to lower layer. So lower layer applies a viscous force on the upper layer in the backward direction, so as to oppose the relative motion between the layers. And by Newton's third law, if the lower layer applies a viscous force on the upper layer in the backward direction, the upper layer will apply a viscous force on the lower layer in the forward direction. Same magnitude, opposite direction. Now we say that since there is a velocity differential of dv in a distance dx, we say a velocity gradient is produced. What is gradient? The rate of change of anything with respect to length. When I say velocity gradient, so the velocity gradient means the change in velocity upon the distance. So dv by dx. So Newton's law of viscosity says that the force acting between the layer is directly proportional to the velocity gradient. The greater the velocity gradient, the higher will be the viscous force. The lesser the velocity gradient, the lower will be the viscous force. So the force is directly proportional to the velocity gradient, and the force is also directly proportional to the area in contact between the layers. The greater the area of the layers we are considering, the greater will be the amount of viscous force. What do physicists do every time they find some proportionality? They add up a proportionality constant. So we say the force comes out to be equals to neta A dv by dx. What is neta? It's called viscosity. What is F? The viscous force acting between the layer. What is A? The area of the layer under the consideration. The greater the area of layer we consider, the greater will be the viscous force acting between them. And what is dv by dx? It's the velocity gradient, the rate of change of velocity with respect to length. So now remember that this quantity neta is the viscosity. Now viscosity depends upon what? The type of material and temperature. For liquids, on increasing the temperature, the viscosity decreases, and for gases, on increasing the temperature, the viscosity increases. Now, many a time people say that viscosity is nothing but fluid friction. But do understand the viscous forces are different from the frictional forces. How? When you have got a block moving on a surface, let's say with a speed v, I ask you which type of friction force will act. You will say, sir, the kinetic friction force. How much? Sir, if it has mass m and here the friction coefficient is mu, that will be mu mg. Do the friction force acting depends upon the velocity of the block? No. Kinetic friction force has a constant magnitude. It's just depend upon that there should be relative motion between the bodies. Right? So, friction force do not depend upon the magnitude of the relative velocity. Friction force do not depend upon the magnitude of the relative velocity. But beta, viscous force depends upon the magnitude of relative velocity. The greater will be the velocity change over a given length, the greater will be the amount of viscous force. The second difference, friction force is independent of the area of contact, but viscous force depends upon the area of contact. So definitely viscous force are different from frictional forces. Why? Frictional forces do not depend upon the magnitude of relative velocity. Friction force do not depend upon the area of contact, while viscous force depends upon both of them. So viscous force depends upon relative velocity between the layers and the area of cross section, the area of the layers we are considering, unlike the friction force. Now here is one important thing that you should know. The SI unit of viscosity is Pascal second. Sir, how do you get Pascal second? See here. We can say viscosity equals to force upon area into dx by dv. Now force upon area becomes beta Pascal. So you get Pascal, force per unit area, SI unit is Pascal, pressure. And dx represents length and velocity represent LT minus 1. So you cancel out this length and length, you get Pascal into time. So the time has got SI unit of second, hence the SI unit of viscosity is Pascal second. but in the questions they will always give you the viscosity in the CGS unit. I don't know why, but they do it every time. So the CGS unit of viscosity is poise. The CGS unit of viscosity is poise, and in the numericals they will give you like the viscosity of this fluid is 0.3 poise, and you need to solve the question. So as to solve the question, you need the viscosity in SI unit, but they will give you in the CGS unit. So it's very important that you know how to convert from CGS unit to SI unit. So tell me, in SI system, we take beta kg, we take meter, we take second. SI unit are bigger compared to CGS unit, right? So remember that for viscosity, 1 SI unit equals to 10 CGS unit. 1 SI unit, 1 Pascal second equals to 10 poise. 1 SI unit equals to 10 CGS unit. 1 Pascal second equals to 10 poise. So keep this particular thing in mind. So if in question they give you that the viscosity of this particular fluid is 0.3 poise, do not write it while solving as 0.3. No, substitute it in SI unit. Now 1 poise equals to 1 by 10 of SI unit. So write it as 0.3 into SI unit by 10. So you will get 0.03 as the value of viscosity in the SI unit. So this particular conversion is super duper important. Okay. Now moving on to only one question to practice on viscosity. So let's say there is a lake and the lake has a depth d, and at the top of the lake we have a boat moving with a speed v. If the area of contact of the base of the boat with the fluid is A, question is what is the force that has to be applied so as to keep this boat moving with a constant velocity. So assume a linear velocity profile, determine the viscous force on the boat, or how much force you have to apply in the forward direction so as to move the boat with a constant velocity. The forward force that has to be applied has to be equal to the viscous force by the fluid. Now how much viscous force will act? At the base of the lake, we will say that the velocity is 0. At the top layer, which is in contact with the boat, will have the same velocity. The velocity gradient created here is the rate of change of velocity with respect to length. In a length d, the velocity changes from 0 to v. So the velocity gradient will be nothing but v by d. So the force acting will be equals to the viscosity times the area of the base of the boat multiplied by v by d. So the force acting equals to neta viscosity into area of the base of the boat into the velocity gradient, which is as the velocity changes from 0 to v in a length d, the velocity gradient will be v by d. So if you need to plot the graph of how much force has to be applied to keep it moving with the constant velocity, or how much is the viscous force versus the velocity of the boat. So the graph comes out to be a straight line because the force required is directly proportional to the velocity. They might ask how much power has to be delivered to the boat so as to keep the boat moving with a constant velocity. So you will say the power required to move the boat with a constant velocity is that the force acting on the boat should be equal to the viscous force. Now we know that the force that has to be applied to keep the boat moving with a constant velocity is neta av by d. So we will say the power has to be equal to the force times velocity. So neta av by d into v, that is neta av square by d. It is so simple. If they ask you what will the graph of the power delivered to the boat versus the velocity of the boat will look like, so you can see p proportional to v square. So if you need to plot the graph of power that is needed to be provided to the boat so as to move it with a constant velocity v, you get p proportional to v square. So the graph goes something like this. P grows faster than v. So now let's talk about Stokes law, and that will take us to the terminal velocity. Let's say we have got this fluid molecules which are at rest and an object is moving through the fluid. The fluid applies a force on the object in the direction opposite to its velocity relative to the fluid. So since the object has got velocity towards right relative to the fluid, a drag force, a viscous force will act in the direction opposite to the velocity. So the drag force acts in direction opposite to the velocity of particle with respect to the fluid. Now Stokes law gives us the idea that how much is this force and how to calculate it. So we have found that the force acting on the particle is directly proportional to the radius of the particle. We have also found from experiments that the drag force is directly proportional to the velocity. So faster the particle moves, the higher is the drag force. If the speed of the particle doubles, the drag force doubles. If the speed of the particle triples, the drag force triples. That is the meaning of the drag force is directly proportional to the velocity of the particle with respect to fluid. And we can say every time we get something like this, we add up some proportionality constants. So we get the drag force to be equals to 6 pi neta RV. What is 6? So 6 you know is 6 pi 3.14 22 by 7. Neta is the viscosity of the fluid. R is the radius of the particle moving through the fluid and V is the velocity with which it moves. So the drag force comes out to be 6 pi neta RV. One more time, the drag force applied by the fluid on this particle is equals to 6 pi neta RV. 6 pi neta RV. Here we are talking about spherical particles of radius r. So moving on. Now let's talk about something called terminal velocity. Now what is terminal velocity? The ultimate velocity. This is my personal favorite question to ask from students. The acceleration of a particle is given by 6 minus 3v. Determine the terminal velocity of this particle. The acceleration of a particle is given by 6 minus 3v. Determine the terminal velocity of the particle. So see, initially let's say velocity is 0. So acceleration will be equals to 6 minus 3 into 0. That will be 6. Because of this acceleration, the velocity will start to increase. But as the velocity will start to increase, the acceleration will start to decrease. Tell me, for which particular velocity the acceleration becomes 0? So sir, acceleration becomes 0 when the velocity becomes 2. So initially, when there was no velocity, there was an acceleration of 6. As the velocity will keep on increasing, the acceleration will keep on decreasing. And when the velocity becomes 2, the acceleration becomes 0. And once the acceleration becomes 0, the velocity becomes constant. So once this particle or whomsoever motion I am defining, once its velocity becomes 2, its acceleration becomes 0 and then it keep on moving with the same velocity of 2 meters per second. So sir, what are you trying to explain here? Terminal velocity is the final velocity. As a raindrop is formed, it has no velocity. So no drag force acts on it. When the raindrop is formed, initial velocity is 0. As we know that the force of drag is 6 pi neta RV, as the initial velocity is 0, the drag force is 0. But as the raindrop starts falling down, the drag force on it starts increasing because its velocity keep on increasing. At a particular instant, the drag force becomes so large that it is equal to the effective weight of the drop, and then the net force on the drop becomes 0, and hence the acceleration of the drop becomes 0. So the drop falls down then with a constant velocity, and this constant velocity is called the terminal velocity. So when the raindrop is formed, it has got no velocity, and since it has got no velocity, there is no drag force acting on it. Now, but as the particle falls down, its speed increases and so does the drag force. Once the raindrop attains terminal velocity, the final ultimate velocity, if it is moving with an ultimate final constant velocity, then the acceleration has to be 0. Its velocity becomes constant, and once the terminal velocity is attained, you can say that the acceleration of the raindrop will be 0. If you know that once the raindrop has attained terminal velocity, a constant velocity, its acceleration is 0. So if the acceleration is 0, the net force also have to be 0 now. So the net force on the raindrop has to be 0. So just remember this line in the box. Once the terminal velocity is attained, terminal velocity, the final constant velocity, the acceleration becomes 0. And when the acceleration becomes 0, you can say that the net force has to be 0. So now deriving the formula of terminal velocity. The formula of terminal velocity, let's say there is this raindrop or particle which falls through a fluid of viscosity neta having density sigma with a terminal velocity Vt. When the particle falls down with this terminal velocity, what will be the forces acting on this particle? So there has to be force of gravity. And the force of gravity will be equals to mg. And the mass of this object can be written as the density of object multiplied by volume of object. So rho into 4 by 3 pi r cube. This will be the force of gravity. If the surrounding fluid has a density sigma, the surrounding fluid will apply a force of buoyancy. How much is the force of buoyancy? The density of surrounding fluid, which I am saying to be sigma, into the volume submerged, the volume of this whole drop, which is 4 by 3 pi r cube into g. So this will be the force of buoyancy. As well as, in addition to these two forces, there will also be force of drag. In which direction? Opposite to the direction of velocity, upward. And that will be equals to 6 pi neta rv. For equilibrium, if the particle is falling with terminal velocity, the net force has to be 0. So the force of gravity has to be equal to upward force of buoyancy plus the upward force of drag. The net force in downward direction equals to net force in upward direction. Now substituting their values, we will get rho into 4 by 3 pi r cube into g, the force of gravity, equals to sigma into 4 by 3 pi r cube into g, the force of buoyancy, plus 6 pi neta rv, the force of drag. Now moving this whole term to the left hand side and cancelling out some terms. Here beta, you can cancel out pi, pi, pi. One term of r with here, so here you will get r square, or before that I will say bring this whole term to the left hand side and take 4 by 3 pi r cube into g common. So you will write rho minus sigma, bringing this whole term sigma into 4 by 3 pi r cube into g to the left hand side, rho minus sigma into 4 by 3 pi r cube into g equals to 6 pi neta rv, and we have cancelled out one r from here and one r from here, so that's why it's written r square. So from here now you can cancel out this 6 with the 4, so you get a 2 here and a 3 here. The 3 goes in the denominator, so you get v equals to rho minus sigma, and the pi get cancelled, into 2 by 9, and there is an r square in numerator upon neta, and there is a g in numerator again. So you get v equals to 2 by 9 rho minus sigma r square into g by neta. So this is how we derive the formula of terminal velocity. Now you need to remember that the terminal velocity of the particle is directly proportional to the whole square of radius. The terminal velocity of particle is directly proportional to the whole square of its radius. So terminal velocity proportional to r square. So if the radius of the particle becomes double, the terminal velocity becomes 4 times. If the radius of the particle becomes triple, the terminal velocity becomes 9 times. The terminal velocity is directly proportional to the whole square of radius. Keep this thing in mind and utilize this to solve the question coming up. So the question goes like, if a raindrop of mass m falls with a terminal velocity v, then the raindrop of mass 8m will fall with how much speed? So if the raindrop of mass m falls with a terminal velocity v, raindrop of mass 8m will fall with how much speed? So sir, we know that the terminal velocity is proportional to the radius whole square. We need to compare the radius of these two drops. How to do? We can say that the first drop has mass m, the second drop has mass 8m, 8 times the mass. And we can write the mass of the drop to be equals to the density of the drop into volume of the drop. We know that the mass of the drop is proportional to r cube. The mass of the drop is proportional to r cube. So if the radius of the drop becomes double, mass becomes 8 times. Radius of the drop becomes triple, mass becomes 27 times. The second drop has 8 times the mass. So the second drop will have double the radius. So if the first drop has radius r, then the second drop will have radius 2r. And when the radius becomes double, the terminal velocity becomes 4 times. So if the mass is 8 times, the radius has to be 2 times. If the mass of the second drop is 8 times, mass is 8 times, then the radius of second drop has to be 2 times. As the terminal velocity is proportional to r square, since the second drop has double the radius compared to first drop, it will have 4 times the terminal velocity. So as the radius becomes double, the terminal velocity becomes 4 times. So that's all in this hour. See you guys in next hour where we will talk about surface tension. So that's all for now. See you guys in the next hour.